So picture this. You walk past an old brick building on your street, right? The facade looks completely normal, maybe even charming.
Yeah, but under the surface, it's a completely different story.
Exactly. Because according to the research we are diving into today, an article titled Fortifying the Foundation, Modern Building Strengthening Techniques, that building's hidden skeleton could actually be on the verge of a catastrophic collapse.
It's a terrifying premise, honestly. The exterior looks totally intact, but the structural integrity is just quietly compromised by decades of subtle degradation.
Right. And that brings us to our mission for this deep dive. We want to understand exactly how engineers step in and stop these invisible disasters.
Right, because you can't just patch up the masonry and call it a day.
No, you really have to fix the building's hidden skeleton while the whole structure is still standing.
You do. Engineers specifically have to target the weak columns and beams. That's the core load-bearing framework.
Wait, let's unpack this skeleton analogy. If you have a skeletal structure that is already exhausted and, struggling to hold up the building's weight, how exactly do you reinforce it?
Well, the answer lies in a specialized engineering process called building strengthening. Historically, that meant bringing in heavy steel plates and just bolting them directly to the vulnerable concrete.
Wait, hold on. If you bolt tons of thick steel plates to it, doesn't that just add a massive amount of dead weight?
It does, yeah.
Like you were essentially asking a failing column to carry its own heavy armor.
That is exactly the engineering paradox here. I mean, steel adds immense strength, but the weight penalty is just severe.
Right.
So that is why the strengthening toolkit has evolved so drastically. It really requires a highly specific toolkit designed to bind and reinforce the existing structure. The source highlights this massive shift toward advanced materials.
Advanced materials like what?
We're talking specifically about carbon fiber wrapping and a process called jacketing.
Okay, here's where it gets really interesting to me. Carbon fiber wrapping. I mean, I know they use that in aerospace labs because it's incredibly lightweight and strong, but for an old brick building.
Yeah, it sounds a bit sci-fi, I know.
It does. And doesn't a column need compressive strength to hold vertical weight up rather than, tensile strength?
It does need compressive strength, yes. But you have to look at how concrete actually fails under extreme compression.
Oh, okay.
When a concrete column is crushed beyond its limit, it doesn't just snap. It bulges outward laterally and then shatters. So the carbon fiber wrap doesn't hold the building up directly.
Oh, wow. I see. So it's less like putting a rigid medical cast on a broken bone to let it rest, and more like, strapping a high-pressure corset around the column.
What's fascinating here is that that's the perfect analogy. When the concrete wants to fail and bulge outward, the carbon fiber wrap, which has immense tensile strength, acts as an unyielding corset.
Because it just won't stretch.
Precisely. It strictly confines the material, so it literally just has no room to break apart. And when we talk about jacketing, we're taking that concept of confinement and reinforcement even further.
So how does jacketing differ from just wrapping it in the corset?
Well, jacketing involves encasing the existing weak column entirely. You are generally pouring a whole new layer of stronger, high-strength concrete around the original pillar.
And you reinforce that new layer too.
Yeah, exactly. Often with those steel plates or carbon wraps we just mentioned, it gives the old column an entirely new, expanded threshold for stress.
Got it. So by combining these traditional materials like stronger concrete and steel plates with the advanced wraps, you are fundamentally altering the physical limits of the existing columns and beams.
You really are. You are drastically increasing the structure's lateral force resistance.
Which is the ultimate payoff for strapping all this steel and carbon fiber to an old building, right?
Exactly. If we connect this to the bigger picture, this isn't just about supporting static weight from the floors above. It is about surviving dynamic trauma over time.
Right, because an event like an earthquake isn't just a heavy weight pushing straight down.
Yeah.
It's, kinetic energy violently whipping that skeleton in every possible direction.
Yeah, when the ground shifts, lateral loads just tear through the vertical columns. Without that confinement from jacketing or wrapping, the concrete fragments.
And that leads to a catastrophic pancaking failure.
Exactly. But the carbon wraps and reinforced jackets dissipate that kinetic energy. They keep the structural core intact, even when the earth trying to tear it apart.
Yeah.
These hidden reinforcements are the literal difference between a catastrophic failure and a building successfully weathering an earthquake.
That is incredible. So the next time you look at a seemingly fragile old building and you wonder how it survived an earthquake or how it's supporting heavy loads, remember what we covered in this deep dive. It is very likely thanks to these hidden structural reinforcements.
Mm-hmm.
The jacketing and carbon plates doing the heavy lifting, totally out of sight.
And I think that leaves you with one last thing to ponder on your own today. So many normal-looking buildings secretly require this intense structural life support just to stay standing. How much of the everyday architecture you walk through is quietly wrapped, jacketed, and plated right beneath the surface?